Hi, I'm James from the School of Maths and Stats, and also here in the Earth Institute. So I'm just going to talk briefly about my research today, what I've been doing for the last few years, work on what we term coastal megaboulders. So what we're talking about here is that if we go to some of the highest energy coastlines, what you'll find is that on some of these cliffs, that are really exposed to the waves that'll come in through storms or basically very big wave events, then what you often find is that there are these large deposits of, well, essentially massive boulders. And you can see one image here, and this is on one of the Aran Islands. And you can see that, well, we are quite close to the shore here, and we're maybe 10 to 20, maybe 30 meters above high water, and maybe 50 to 100 meters inland. And you can see that there is this large collection of very big boulders here. And these can range in size of tens to hundreds of tons in weight. And they fit into maybe the dimensions of perhaps a couple of meters to half a meter in the different dimensions of the rocks themselves. So when you think about, what does that really mean? That could be like if you had, 100 cars, but then squeeze them all into the space of just one car. It's that kind of size and density, really, and weight to these things. And so there are many of these deposits all around the world, but what's kind of special about Ireland is that there are many of them, a very rich set of these boulder deposits on our west coast. Especially around the Aran Islands, but also in other locations. And sorry, I'm just trying to, I might just. So what's very interesting about these is that they're observed to move around these huge objects. So here's an example of one boulder that is, it's nearly 130 tons in weight. You can see on the right there that it's one of its kind of smallest dimension is the height of a person. It's 50 meters inland and it's 14 meters above the kind of the typical water height. So, but what was seen between 2 years is that this massive 130-ton boulder was moved by nearly 7.5 meters. So this, is kind of a huge event to happen. And so one of the things so we know that it's the kind of the water and the waves that cause this, but everything that happens between that is a bit of unknown. They're mapped kind of annually, and we see the movements kind of after they've happened. And if we have collections of boulders, we can see some of them have moved and some of them have not moved. And that kind of adds to the little bit of the mystery of what happens here. Well, what is happening is that, especially in places like Ireland, there's big storm events happen almost annually. I mean, we know from the last week that we've had 3, and depending on which news source you're looking at, potentially 4 storms have come. Well, 3 certainly named storms have come in the last week, and those have brought some very significant wave events with them. So these big events happen every year, and there was a very particularly stormy year in 2013-14 during that winter, where there were some really big waves hitting the west coast of Ireland. And this was a kind of a famous picture in the Hinch taken there, and you can really see the waves coming in and smashing against the shore there. And that's kind of the idea of what's happening, or what's kind of the basis of how the water interacts with these boulders. So you have kind of big waves coming in from storms out at sea. They come in and they essentially smash off the cliff tops, and they overtop them, and then you have these sweeping bores of water that hit into the rocks and move them. So these are happening now on well, what we term the highest energy coastlines. If we kind of go back here, this is a very isolated region. People don't live here, and they don't live here for a reason. I mean, it's not an inhabitable zone especially during winter. But as we're seeing more and more wave events, especially stronger wave events in more inhabited regions, it's very important to understand what are the effects that waves impacting coastlines can really have, and what can we really understand about the highest energy events. And these are certainly among the highest energy events out there. So I started off as a postdoc on a project to kind of understand these nearshore wave events, while also looking at these coastal boulder movements. And this was a very nice project that brought together researchers from very different disciplines. So there was us here in UCD, led by Frederick Diaz, working on the kind of wave mechanics and the modeling of the boulder movements. There was Rona Cox, who's also an Earth Institute affiliate member, but based in the US as well. And she's the geologist in the group, and did all the field work and all the boulder movement mappings and photogrammetry and all that geology aspects. And then there was a group in Belfast that were engineers, and they worked on kind of wave tank experiments and setting up other field instruments to measure a lot of the dynamics that go on here. And well, we're really just one group of many groups that study this. So there's other groups between the US and Japan. There's other groups between Germany and Australia, and lots of different places around the world are kind of looking at this problem a little bit disconnected, but at the moment these networks are growing, and we're starting to talk amongst each other and really come together to tackle this problem. And so here's a nice image of our group on a field trip, and you can really get an idea of the scale of some of these boulders that are moved around. And this thing that we're all sitting on with plenty of room to spare, and this was moved around a few years ago. So it gives you an idea of just the size of these rocks that get moved in the wave events. So our contribution is from the kind of mathematical aspect. So we're kind of dealing with a few fundamental questions to do with the models that deal with this fluid structure interaction. And well, one of the main kind of questions that's out there and debates in this field, and it's a fairly young field in terms of intensive study, is whether tsunamis or storm waves cause these movements. And for sure, tsunamis cause them, and there's lots of documents of tsunamis causing these. We even observed lots of huge mega boulders being moved in the Tohoku tsunami in 2011, for example. But in Ireland, there hasn't been a tsunami hitting the west coast of Ireland since, I think, 1755 with the Lisbon tsunami. So with the movements that are observed almost every year in Ireland, the cause and what we say is the definitive cause are storm waves. And there's a lot of debate in the field about this. And really, the reason why there is debate is because there's a lack of understanding of a lot of what are the next 2 points here, which are really the hydrodynamic kind of force balance relationships that people use to model these movements and interactions, and especially also the kind of roles of impacts and impulses. So when you have like a large body of water, and people kind of underestimate the sheer weight and force that a large body of water would have when it hits an object, then fluid is really accelerating in lots of directions. It would really give a kick to anything. If you just think of standing in the nice calm sea when it's just a little wave coming towards you, then it still knocks you back a little bit. But these are violent events that are happening. So our role is really kind of understanding and fine tuning and unpicking a lot of these modeling, trying to develop them and come up with some justifications and find some of the real understand and fit the parameters of the problem. So I'll just give you an example of some of that from the hydrodynamic modeling. So there's a few different physical parameters that would exist in the problem, such as the friction between the boulder and the ground as it's going to move, and things like hydrodynamic drag and lift. And so here I'll just talk a bit briefly about the lift coefficient. So we won't go into really where it comes from, except the one thing you should know is that the larger the lift coefficient, then the easier it is to move these boulders. And there's kind of one particular number that has become all pervasive in the literature, and it's saying that this lift coefficient is 0.178. So if you track this back, and it takes quite a while because it appears in many papers as kind of the lift coefficient for this problem, but you get back to a paper from a couple of papers from the 50s and 60s, and essentially it comes from an experiment done with spheres that are nearly 7 centimeters in diameter. Now, the boulders that we're really looking at are certainly much bigger than 7 centimeters, and they're not spheres. So this kind of number is really, it's become kind of all pervasive, but it doesn't make much sense. And you can argue really that a lot of the debate between storms and tsunamis can come down to this particular number. It's one of the ones that people use to really justify that these things can't be moved by storm waves. But, well, what I'm trying to argue here is that it's not a relevant number to use. And there's a really nice paper that I often come back to from Rover et al. In 2017, where they took a boulder deposit in the Bahamas, and they basically said, we have this deposit, lots and lots of rocks. What could have made this? What are the environmental parameters that would have made this deposit? And then they came back with essentially, by looking at all the different rocks there, they came back with a distribution for what the lift coefficient could have been for the different types of flows and such that could have caused this deposit. And they have a much larger range of lift coefficients. Essentially, there's very few of them that would have been less than 1, and then the bulk of them are between 2 and 3. So we're talking an order of magnitude greater than what is seen in the literature. And then myself and Frederick did a study, a fluid mechanics study, where we were also calculating this lift coefficient by flow over these boulders. And what we see here is just what's plotted on the x-axis in the bottom left here. The x-axis is just the aspect ratio of the boulder. It's kind of length to height. So just the study for different shapes and sizes of these boulders. And we see that we're getting lift coefficients that are similarly in the kind of 1 to 4 range for reasonably sized boulders. So this kind of parameter is certainly much larger than what's observed, or not what's observed, but what's been used in the past. And this gives a huge boost to the idea of storm waves moving these big boulders. So what we're kind of doing at the moment is trying to really understand these dynamics, and especially understand these parameters that happen hydrodynamically in the fluid structure interaction here when these boulders are transported by waves. So what we have a series of physical models that combine drag and friction and impacts and impulses that can from very short, sharp impacts. And we would also have some experimental data from experiments of this, and hopefully we can get some field data. It's something that the networks that are kind of coming together now are really trying to be able to observe these in the field, and really real-time observations of this. And so what we'd like to do is use our physical models and the data so that we can kind of really allow the boulders to tell us how they move. So instead of us, trying to say, oh, what if we this coefficient, that coefficient, this number, what will happen? Try to really use the models and the data with some level of uncertainty quantification to be able to fit these parameters and really understand what's going on. So that's kind of ongoing work, and hopefully future work will be even more involved in that aspect. And the kind of outlook of this is really, our coastlines are very vulnerable, and we're really trying to understand what's going on here, because it's not an easy problem. There's a lot of unknowns, and what we want to do is to be able to understand some of the fundamental dynamics, like really understand what's going on, and then with that process, hopefully, then we could potentially be able to make predictions on what could happen, not just on these exposed coastlines, but also maybe in more kind of inhabited zones, and be able to really understand and be able to quantify levels of damage that can be done by storm waves in other situations. So that's just a summary here of my work, and not just my work, but work of a vast array of colleagues as well. So hopefully I've given you a good idea, and happy to take any questions.
Okay, thanks, James. Is there any questions from the room first for James?
So do the boulders just suddenly move, or is it just like a little creep most of the time?
Well, that is an unknown. No, that's it. It's very important. So when we see them after the fact, so there could have been a series of storms, and there could have been a lot of small movements. There could have been one big movement. I mean, statistically, you might say it's probably just one big movement, but it's very hard to say, because you see boulders, one of them has moved and the one next to it has not moved. But then, so even within one storm, was it one wave or was it many waves? I mean, these are all open questions, and really in situ kind of experiments are really what's going to answer that.
And like, can you do time lapse or? So can you do like a little time lapse, like a really boring video of like a boulder maybe moving, not moving, or can you put like a little like GPS tracker on it and see has it moved, or is that a bit mad?
No. It's the problem with it is that if you put something there, if this is moving a 50-ton boulder, it's going to absolutely destroy whatever camera you might have there, or potentially could. And there's not really, I mean, there's an idea that there's kind of a story that someone has seen these boulders move, but from like a lighthouse on these kind of rocky platforms. But even observing it is not as easy as you might think, because when the water's over it, all you see is the white foam, and it's not so clear what's happening. But the idea of putting kind of little accelerometers onto these boulders is definitely one that we'd like to do. But the problem is that you might have to put it on a load of them, because you don't know which one may move. But yeah, exactly. Yeah.
Any more questions? If not, I'm going to wait until people think of ones. I'm going to ask a few. Firstly, what's the source of the boulders? Do you know?
Oh, you can kind of see it a bit on the last slide I had up. Can we put it back up? Or so the bedrock that's there is a kind of a limestone bedrock.
Okay.
And then there, between the layers of limestone, there's these little shale layers.
Okay.
And so these little shale layers get eroded out, and then basically the resulting exposed and further exposed limestone is then just kind of hydraulically fractured out.
Okay, so it's sort of pushed up.
Yeah.
Okay, I was wondering, was it coming from seabed or something like that? I was going to say that's huge forces.
Yeah. So you can kind of see how there's these little steps here. Yeah. And these little steps are, it's almost like it's peeled back, kind of the bedrock. And it's remarkable if you're ever out there in the Aran Islands, it can be a remarkably flat platform with these little steps every now and then a big boulder deposit behind it.
Yeah. Any more questions from the room? If there's no questions from the room, is there any questions from people online?
This beam no longer exists. It fell into the water.
I think Peter has a question there.
Hi there. Can you hear me? Can you hear? Yeah. Anyway, I'm going to ask my question. I'm not quite
Fire
sure.
away, Peter.
I'm not quite sure whether you can hear or not. Almost exactly this time last year, I was out in Clare trying to shoot video for virtual field trips for our students. So I was up in the Burren, but further south around Kilkee as well. And there were some of these big boulders there at both locations, in fact. But the thing that intrigued me was that they were obviously moved quite recently because they'd left fresh scratch marks. So you could actually see how they'd been moved over tens of meters, the kind of trajectory of the boulder. And it just strikes me that that might be quite interesting information to, feed back into the sort of the modeling work. I did shoot some video of the track, so I will try and find that and send it to you. But yeah, so I mean, this time of year might be quite interesting time to go out and see what, well, particularly those last big storms, if they were big enough, whether these tracks have been left as well. But it did imply in this case that, these boulders weren't lifted completely off the platforms. They were scratching their way across them. Anyway, just a different insight into them.
Yeah, no, that's definitely a key feature, these scratches. And there's a colleague in Trinity who's spent time actually quantifying these kind of erosions by those kinds of scratches. And apparently, if you sum up a lot of these, you get a remarkable amount of total erosion just from the scraping along. It's really a huge quantity that could be ultimately eroded from the bedrock. But yeah, we've also seen these scratch marks, and well, they will last for a while, but they would also be eventually covered up as from a fresh scratch mark. It will eventually lose that signature.
Yeah, perhaps the largest structures that man-made structures that move are ships. So basically, if you want to move them, you just float them out. So how much is the buoyancy factor in this movement of the rocks? Say you have something like that, then just floats up, then it does not have any friction.
So, like, if you mean like if the platform was flooded and then yeah, so the kind of buoyancy is a factor for sure. But it comes down to whether, I mean, if it's just a bit flooded, it'll still be fairly still, but then it might just be the big impact of a body of water hitting it to translate it across. But the
Water flows and beneath the pivot, then it floats up.
Yeah, well, it wouldn't float up, but it would. There is a buoyancy effect for sure. Yeah. And I mean, I'm doing a little bit at the moment of kind of trying to look at what might be termed in fluid mechanics as a mixed lubrication model for these kinds of slidings.
In that sense, in that situation, does the kind of intense pressure and speed of the water underneath them make a big difference to the likelihood that they'll be lifted and pushed along? You kind of said, when the wave breaks, everything gets forced into cracks and under really intense pressure. Does that change that kind of buoyancy effect, if you like?
I think it certainly would. There's certainly also not enough work done on that, and it would especially be not just the liquid getting in, but kind of enhanced by the trapped air pressures and stuff as well inside there. And that's, I mean, speaking loosely, that's a very messy problem, and it's certainly one that's very difficult to just give a straight up answer to. But dynamically there would be a lot going on, and it would all contribute to making the movement easier, I think.
Is there any more questions online or in the room? Yes.
I was curious whether other people are working on similar problems in different contexts. I guess this I mean, are there other applications for this kind of work? Are there other people grappling with these kinds of questions with quite different sort of situations and outcomes?
I'm not sure exactly. I know that there are people that do work kind of on landslides. That'll be a different form of transport of large rocks, not kind of by wave action, but by friction and gravity, really. But certainly, I mean, in terms of the fluid mechanics and geology and coastlines, it's, I'm not sure that there's I mean, I can't give an exact answer, but I'm not sure. Sorry, on the spot.
Yeah, I'm sorry.
No. Sorry.
I mean, I thought in the context of transportation and things like that, it's potentially something that people look at. I mentioned that kind of situation. Maybe there are similar kinds of issues.
I've seen a few nice papers. One that was kind of talking about how some of these, ancient constructions were done and how people transported big blocks across. And I mean, there was one from in China where essentially they used the frost and ice in the winter to be able to drag the blocks across, and using that reduced friction to be able to transport big things. But that's a very different thing that was going on. Yeah.
Just one more question. I have one question. They're limestone boulders. So limestone is very pitted and there'd be lots of gaps. So you wouldn't actually have a very smooth surface with limestone resting on limestone. So they could be full of water a lot of the time just from normal rainfall. So you might need that much overtopping to actually increase the buoyancy force to move them. Is that included in your model?
I would say they can be remarkably cube in shape. I mean, there is, I don't have one there, but there's one where there was a fresh boulder that was fractured out, and it was incredibly straight on that, because it's a very brittle rock as well, so it just fractures. I mean, it doesn't. It's not really malleable or anything. But what maybe to build on that, essentially, if you ever go there in the winter, I mean, it's very slimy and slippery, so that would add even more to reducing frictions and things like that. So there's a lot of extra features as well.
Yeah. So if there's no more questions, I don't think there's any. Is there any more questions online? No, I just see one shake of the head. So at that, I'm going to call end to the first hybrid coffee morning. I imagine this is going to continue for a while. No, Will is shaking his head that this will not continue for a while. So with that, I'm going to thank. We're going to thank James again, and see you all soon.